This is Galileo Galilei. 500 or so years ago, Galileo started to look at the physics and mathematics of falling bodies. He is credited with having the idea of making the job simpler by diluting gravity by looking at inclined planes rather than bodies falling straight down. We have set up an inclined plane here. The white thing is a small portable whiteboard, which we've laid on a flat surface and tipped up slightly using a couple of CD cases. The falling body is going to be this ball bearing. We're measuring the position of the ball bearing using an ordinary steel tape. The tape is fixed to the inclined plane using a bit of tape, and I'm preventing the ball starting to move with this pencil. The apparatus is completed by the timer embedded in a smartphone. So position will be measured using the tape and time will be measured using the timer on the smartphone. We have not made any attempt to start the position from zero or the timer from zero. This doesn't matter, we can sort all that out later on when we come to recording the results. That all happened rather quickly, so let's have a look at the same thing in slow motion. Even that was a bit fast, so what we're going to do now is insert some freeze frames. What you need to do is record the position of the ball as measured by the tape and the reading on the timer. It is of course perfectly okay just to use pencil and paper to record the results, but we have decided to use a spreadsheet. This can save quite a bit of time in applications like this, and you would be well advised to become thoroughly familiar with the way spreadsheets can be used. Column A is recording the time in seconds as read from the smartphone. You almost certainly should have exactly the same results as I've got here. The distance part of the measurements is not quite so easy. This is because the tape measure is fairly finely graduated, and also the problem of parallax. We won't go into details about what parallax means, but you probably found it difficult to measure exactly where the ball had reached at the later times in particular. Next, we need to deal with the fact that we started neither the timer nor the distance measure from zero. The extra columns D and E are going to do this. So I've started the elapsed time and the distance moved at zero. The other quantities here are calculated by formula, which you can see here. This elapsed time is merely the difference between the figure in cell A3 and the figure in cell A2. The use of the dollar sign is a technicality here that's very useful, as it enables me to copy this cell formula into this cell here and to have the cell address here move to the next row and the cell address here be fixed at the starting time. Next, we will want to look at this as a graph. Completely in order, of course, to use graph paper and manual graph plotting, but the spreadsheet will do a good job for us, so that's what we've chosen to do here. And you use charts, and the chart I've chosen is a scatter graph. You can choose other ones, but this gives, I think, some of the best results. I have also chosen to add in a trend line, which you will find in amongst all the instructions for drawing charts. The chart we've produced is actually quite a good representation of these data. You will see if you look closely that the trend line does not exactly go through all of the points, but these are pretty good, and we're ready to move on to the point of this exercise, which is to ask the question, How steep is this graph? You will almost certainly have been asked the question about the steepness of a line before, but only probably in the case of straight lines. You will have used the gradient triangle and rise over run method. The point being that when you're using a straight line, the size of the triangle and where you put it on the line doesn't matter. You will always get the same slope. That is not the case when you come to doing curves. In the case of this curve, imagine that you're a hiker trying to walk up this as a hill. If you start down at the bottom, you will find yourself on level ground. The gradient is effectively zero. As you begin to walk up the hill, however, it gets steeper. The further you go, the steeper it gets. This is, of course, reflecting the fact that as the ball moved down the slope, it went faster. It covered more distance in the same amount of time. When dealing with curves, therefore, we have two distinct extra problems that we did not have with straight lines. The first is that it depends where you are on the curve, what answer you should expect. On this one, we will get smaller gradients down the bottom left and bigger gradients at the top right. Again, reflecting the fact that the ball gets faster and faster as it moves down the slope. The other problem is, of course, what on earth do you mean by the slope of a curve? How do you actually get to a figure for that? And this is the very difficult problem that Isaac Newton encountered when he was first considering this. We're now looking at the part of the graph that's close to this red point, and we're going to do gradient triangles, much as you would do if this was a straight line. However, we need to do more than one. Starting from the red point, I have moved 0.3 of a second to the right, and I have created a gradient triangle above the point, and I have proceeded the same amount of time, 0.3 seconds to the left, and I have made a blue gradient triangle below the point of concern. As you can see, the gradient of neither of these triangles matches the gradient of the curve. It seems fairly obvious that the gradient of the yellow triangle is too big and the gradient of the blue triangle is too small for whatever the correct gradient of the line at the red point is. Next, we want to calculate the slopes of the lines implied by these two triangles, the yellow triangle and the blue triangle. To help us do this, we're going to need rise over run, and I'm going to put on an extra finer grid so that we can make the rise and run measurements we need. I've done this, so I will add them in. We've got a rise on the yellow triangle of 163 and a run of 0.3, giving us a gradient of 543. And on the blue triangle, we have a rise of 88 and a run again of 0.3. And so we have a slope there of approximately 293. Look at these figures because it's important to realise that none of them are the answer we seek. However, 293 is too small for the gradient we're looking for, and 543 is too big. This is not very satisfactory, so how are we going to do better than this? The answer is to zoom in and make smaller gradient triangles. We're in quite a bit tighter on this now, and I'm going to add an extra gradient triangle both above and below. Instead of going 0.3 to the right and 0.3 to the left, the next triangles go 0.1 to the right and 0.1 to the left. Before we do any calculation, just take a look at this. The two gradients that we've got are still, the situation is that the yellow one is too big and the blue one is too small. However, compare the two triangles. The yellow one is now a better approximation to the answer, and the blue one is also a better approximation to the answer. It is like we are closing a sandwich on a filling here. We've still got an answer that is too big and an answer that is too small. but when we've done our calculation, the answer will be better. This is the fundamental idea that people find difficult in understanding this part of the course. It's very well worth taking the time to look at this and make sure you've got as good an idea of what's going on here as possible. All we need to do now is to do the arithmetic for this, so I will replace the finer grid and the calculations that we need are done also, and we will find a rise on the yellow triangle of 45 and a run of 0.1, and on the blue triangle we have a rise of 35 and it's still a run of course of 0.1. Our two gradients are now 350 and 450. This is a smaller range. Summarising, what we've got now is we know the true answer that we have is somewhere between 350 and 450, and so we would probably say right now we think that the correct answer to our question, how fast was the ball going after half a second of travel, is 400. 400 watts. Well, our units of distance are millimetres and our units of time are seconds. So 400 millimetres per second. If there had been a small speedometer inside the ball, we can now reasonably confidently say that it would have been reading 400 millimetres per second after half a second of travel. It's worth also noting that we're doing a measuring from a graph exercise here. Almost all the examples you will see will be when you know the equation of this curve. You will be able to calculate the coordinates of all of these points exactly, and therefore your rise and run, your values for the upper and lower gradients will be exact, and you can carry on this process as far as you like, getting better and better answers. This is why we are confident that the technique of using limits in calculating these gradients works.